Today we shall study on light source material. The semiconductor material that is used for the active layer of an optical source must have a direct band gap. In a direct band gap semiconductor, electrons and holes can recombine directly across the band gap without needing a third particle to conserve momentum. Only a direct band gap material is a radiative recombination sufficiently high to produce an adequate level of optical emission. The most important of these are the so-called third and fifth material. These are made from compounds of a group 3 elements and a group 5 element. Various ternary and quaternary combinations of binary compounds of these elements are also direct band gap materials and are suitable candidates for manufacture of optical sources. For operation in the 800 to 900 nanometer spectrum, the principal material used in the ternary alloy Ga1-X, AlX, As. The ratio X of aluminum arsenide to gallium arsenide determines the band gap of the alloy and correspondingly the wavelength of the peak emitted radiation. The value of X for the active area material is usually chosen to give an emission length of 800 to 850 nanometer. At longer wavelength, the quaternary alloy In1-X GaX As5 P1-Y is one of the primary material candidate used. By varying the mole fraction X and Y in the active area, LED with peak output power of any wavelength between 1 and 1.7 micrometer can be constructed. The alloy GaAlAs and ion GaAs are chosen to make semiconductor light sources because it is possible to match the lattice parameters of the heterostructure interface by using a proper combination of binary, ternary and quaternary material. A very close match between the crystal lattice parameter of the two adjoining heterostructure is required to reduce interfacial defects and to minimize stains in the device as the temperature varies. The factors directly affect the radiative efficiency and lifetime of the light source. Using fundamental quantum mechanical relationship between E and frequency V, E is equal to h into V. If lambda is given by G by V, then substituting for V is equal to C by lambda, E will be equal to h C by lambda. The peak emission wavelength lambda in micrometers can be expressed as a function of the band gap energy Eg in electron volt by the relationship lambda in micrometer is equal to 1.240 by Eg in eV. A heterojunction with matching lattice parameters is created by choosing two material compositions that have the same lattice constant but different band gap energies. The energy gap or the energy band gap in electron volt for values of x between 0 and 0.37 can be found from the empirical relationship Eg is equal to 1.424 plus 1.266x plus 0.266x square.